From UFOs to possible alien abductions, we're fascinated by the idea of extraterrestrial life. Now, scientists have found the strongest evidence yet that a planet 124 light years away could be home to life.
You know how sometimes you think you've got everything figured out? You've built this beautiful, intricate model and it explains almost everything perfectly. Then, out of nowhere, the universe just throws a cosmic curveball that makes you question everything. Well, get ready, because that's exactly what's happening right now thanks to the James Webb Space Telescope. For the longest time, we pictured the universe as a kind of cosmic toddler, just 280 million years after the Big Bang. It was supposed to be a quiet, dimly lit infant, slowly starting to form its first simple structures. But then, Webb snaps a picture, a truly mind-bending image, and suddenly a Nobel laureate steps up and says, "Hold on a minute. This kid already has a college degree, a PhD, and probably tenure." It's a twist that leaves you wondering, could science really have gotten one of its biggest ideas completely wrong? Just last month, the James Webb Space Telescope, with its incredible infrared eyes, locked on to what looked like just another faint smudge in the deep cosmic field. This smudge was quickly cataloged as MO-MZ14. But here's the twist. Its redshift clocks in at an astonishing 14.44. Now, if you're not deep into cosmology, a redshift of 14.44 might just sound like a number. But what it actually means is that the light from this galaxy began its journey to us when the universe was only about 2% of its current age. Think about that for a second. We're talking about light that left this galaxy a mere 280 million years after the Big Bang itself. That smudge, MO-MZ14, is now officially the oldest object we have ever caught on camera. It's like finding a fossil of the very first single-celled organism on Earth, but in space and from the dawn of time itself. This isn't just any old galaxy. It's a compact, luminous powerhouse, roughly the mass of our own small Magellanic Cloud, but here's where it gets truly wild. It is blazingly bright in the infrared, far, far brighter than any simulation, any model, any theory said a galaxy that early had the right to be. Our cosmic textbooks told us the early universe was supposed to be a much darker, much simpler place. Webb is definitely challenging that narrative. So why is blazingly bright a problem? Well, brightness in a galaxy comes from stars, right? And stars, especially the kind that make a galaxy shine like a beacon, need heavy elements, what astronomers lovingly call metals, even if it's just carbon, nitrogen, and oxygen. Standard cosmology, the lambda CDM model we've all grown to trust, paints a picture of the first generation of stars as these sluggish, metal-poor behemoths. They were huge, they burned fast, and they died young, but they didn't create a lot of the heavier stuff right away. You see, you need several cycles of star birth, death, and cosmic recycling, supernovae exploding, scattering those precious heavy elements back into space for the next generation of stars to form, before enough carbon, nitrogen, and oxygen can build up to make a galaxy shine with this kind of intensity. MO-MZ14, appearing just 280 million years after the Big Bang, should absolutely not have had the time for that kind of complex chemical evolution. Yet, here's the mind-bending part. Its spectrum, the chemical fingerprint of its light, clearly shows emission lines of hydrogen, carbon, and nitrogen. This isn't just a faint signal, it's a robust proof that the place is already chemically seasoned, rich with the very elements that are supposed to take billions of years to accumulate. In plain English, to use one of my favorite analogies, the cake says it baked for an hour, but the kitchen timer, our cosmic timeline, says it's only been 2 minutes. It's a major cosmological crisis, and it's sending shockwaves through the scientific community. This galaxy is emitting large amounts of ionizing photons, playing a role in clearing the fog of neutral hydrogen that characterized the early universe, but doing so with an efficiency that just doesn't compute. This is where the big guns come in. Sir Roger Penrose, a name synonymous with profound insights into space-time and black holes, a Nobel laureate no less, was asked to comment during this week's Cambridge Symposium. And let me tell you, he did not mince words. His statement was direct, impactful, and instantly went viral among cosmologists. His statement was, "If this object is representative, we may need a major rewrite of the early chapters of cosmic history." Now, note the conditional. He's not declaring cosmology dead on the scene, not yet. But he is issuing a serious warning, a red flag that we need to pay attention to. He's saying that the simplest version of lambda CDM, the model that has otherwise been incredibly successful at nailing things like the cosmic microwave background, the afterglow of the Big Bang, is currently under-predicting the number and the luminosity of such giant early galaxies by at least a factor of 10. When the error bars, the uncertainty in our measurements, start to dwarf the actual prediction, you know something fundamental is off. It's like your GPS telling you your destination is 10 miles away, but your odometer says you've already driven 100. There's a serious discrepancy, and it demands our attention. And here's where the problem gets even bigger, even more worrying. MO-MZ14 isn't just a freak outlier. It's not a loner, a one-off cosmic anomaly. Webb has now logged more than 100 similarly remote, similarly bright galaxies at redshifts above 10. Think about that for a second. We're not talking about a single weird data point anymore. Statistically, that moves the conversation from freak outlier to standard population. If the early universe was teeming with massive, chemically mature cities, these bright, complex galaxies, while we expected scattered wooden villages, tiny nascent structures, then our entire timeline of how quickly structure forms, how quickly stars ignite and forge heavy elements, is stretched to the breaking point. It's like discovering that ancient Sumerians had smartphones. It fundamentally changes our understanding of technological progression. This population of unexpectedly advanced galaxies suggests that the cosmic dawn was far more vibrant, far more active, and far more complex than our models ever dared to predict. It's a huge shift in perspective, and it challenges the very foundations of our cosmic narrative. So naturally, when something this monumental comes along, scientists immediately start looking for escape hatches. Could there be a simpler explanation? Could the brightness simply be magnified by a foreground gravitational lens, making MO-MZ14 appear brighter than it actually is? The survey team, being the meticulous researchers they are, already checked. There's no massive cluster, no giant cosmic magnifying glass sitting in the line of sight. So that explanation is out. Could the redshift be wrong? Maybe our measurement of its distance and age is off. Again, the data is robust. The nitrogen and hydrogen lines in its spectrum, which act like cosmic barcodes, give the exact same staggering value. When multiple independent measurements converge on the same extreme number, it means the measurement is solid. Could early stars just be absurdly efficient factories of ionizing photons, burning through their fuel at an unprecedented rate? Maybe, but then we still run into the problem of needing several generations of them to cook metals that fast. You can be efficient, but you can't defy the laws of stellar evolution and nuclear fusion. Every conventional fix, every attempt to patch up the existing model demands something equally extreme, something that feels just as awkward as the original problem.
We're talking about scenarios where either star formation rates were 10 times higher than thought, implying an almost impossibly rapid birth of stars, or tiny halos of dark matter managed to merge into a big galaxy at breakneck speed without shredding their gas. a chaotic, violent process that would typically disrupt star formation. Both of these options poke serious, gaping holes in the gentle, gradual story of cosmic evolution we've been telling ourselves since the 90s. It's not just a minor tweak, it's a fundamental reevaluation of how quickly the universe grew up. Now, you might be thinking, okay, cool, old galaxy, but why does this actually matter to me? Well, here's why. Cosmology isn't just academic navel-gazing. It's the foundation for every other astronomical timescale. It sets the clock for everything. If you shift the age when galaxies light up, you fundamentally shift when planets can form, when chemical enrichment begins, and critically, when conditions for life might first appear. If complex chemistry, the building blocks of life, arrived hundreds of millions of years earlier than expected, if the universe was seasoned with carbon and nitrogen much faster than we thought, then the cosmic window for biology widens significantly. That's not just a scientific curiosity, it rewrites the probability board for life's prevalence across the cosmos. It means the universe might have been hospitable to life, complex life even, far earlier than we ever dared to imagine. It changes our perspective on how unique or common we might be in the grand scheme of things. It's a profound implication that reaches far beyond distant galaxies. So, what's next for this cosmic mystery? The scientific community isn't just sitting around scratching their heads. Later this year, Webb will stare even deeper into the same patch of sky, hunting for Z15, Z16, Z17, looking for even more of these early giants. Meanwhile, the Nancy Grace Roman Space Telescope, set to launch in 2027, is going to blanket 1,000 times more area than Webb, giving us an unprecedented census of the earliest galaxies. We're about to get a truly comprehensive picture of the cosmic dawn. And you know what happens when observations challenge established theories? Theorists get busy. They're already dusting off once exotic ideas, things that were considered too fringe just a few years ago. We're talking about concepts like primordial magnetic fields, which could have accelerated star formation, or ultra-rapid cooling of gas allowing galaxies to coalesce faster. Some are even tweaking the very nature of dark matter itself, proposing new properties that could explain this rapid development. The next 18 months are going to be absolutely critical. They will decide whether Lambda CDM, our beloved standard model, needs minor surgery or full-blown reconstructive work. It's an exciting, slightly terrifying time to be an astrophysicist. If these sorts of breaking space updates, these cosmic curveballs, make your brain light up with curiosity, then you know what to do. The subscribe button is right there. Whack it, and you will ride shotgun with us as this incredible story unfolds. You won't want to miss a single twist. Astronomers, with their characteristic blend of humor and humility, love to say, "We build telescopes to confirm theory," but the universe keeps handing us receipts for things we never ordered. Z14, this unexpectedly vibrant, chemically rich galaxy from the universe's infancy, is the latest, most awkwardly large receipt. It's a powerful reminder that every model, no matter how elegant or successful, is provisional. Every timeline we construct, every grand narrative we piece together, is ultimately just a sketch, an approximation of a reality far more complex and surprising than we can often imagine. It really drives home the point that the cosmos is under no obligation to behave the way our equations find convenient. Just like a century ago, when giants like Einstein believed the universe was eternal and unchanging, only to have Edwin Hubble reveal its grand expansion, we might be at another one of those pivotal moments. It teaches us humility and reminds us that the universe is constantly challenging us, pushing us to think bigger, to question our assumptions, and to embrace the unknown. All right, for those of you already gearing up for the comment section, here's the quick recap, the essential points to arm yourself with. 1. Webb found a galaxy, Z14, at an astonishing redshift of 14.44, meaning we're seeing it just 280 million years post-Big Bang. It's the oldest object we've ever seen. 2. This galaxy is not just old, it's blazingly bright and chemically rich, full of carbon and nitrogen, which completely breaks our standard formation timelines for galaxies. It's way too mature for its age. 3. Nobel laureates like Sir Roger Penrose are publicly worried, not celebrating, because this discovery fundamentally undercuts the reigning cosmological model by a factor of 10. 4. Mumsy 14 isn't alone. Webb has found a whole population of similar rebel galaxies, making this a widespread challenge, not just a one-off anomaly. 5. The proposed fixes for this problem range from impossibly fast starbirth to weirder dark matter theories, but none of them are pain-free. Every solution seems to create another equally extreme problem. So, what does this all mean? Does Mumsy 14, this tiny smudge of light from the dawn of time, kill the standard model of cosmology? Or does it just force us to trade our comfy, old, gradual timeline for a wilder, faster, more vibrant origin story for the universe? Drop your vote, rewrite, or retweak down below, and definitely check back because the next data release, the next batch of cosmic receipts, is only weeks away. You won't want to miss how this cosmic mystery unfolds.